So the purpose of this lecture is to describe what we call the perfectly matched layer. And in numerical modeling, we have a device, we have a wave that hits this device and it scatters and it goes all over the place. Well, that wave eventually reaches the edge of our grids. And what we want to do is handle it so that the wave appears to go off to infinity. Since we can't have an infinitely large grid, the only thing we can really do is somehow absorb the wave at the edge of our grid. That's the purpose of this perfectly matched layer. So we're going to start off with some background information that's going to help you understand the perfectly matched layer. Then the particular one that I'm going to introduce is called the uniaxial perfectly matched layer. Probably the state of the art is the stretch coordinate PML, which I'll discuss at the end as a bonus, but the uniaxial PML definitely has some benefits to it. And it's simple to understand, it's physical, whereas the stretch coordinate PML, as you'll see, we're stretching into imaginary space. And so this is a confusing enough concept to begin with. So we're going to do the uniaxial perfectly matched layer. And once we talk through all the theory, then it's actually a real quick thing to talk about how to incorporate that into Maxwell's equations. And that's where we'll end it here. So the first item on background information is tensors. So we start off with a vector v. If we multiply this by some scalar constant a, all that happens is that we change the magnitude of v. If a happened to be a negative number, then the overall vector will be pointing the other way. So a scalar multiplied by a vector just changes the magnitude of the vector, not its direction. So a tensor now is a generalization to this. We'll start off with the same vector v, but now we're going to multiply it by this thing called a tensor. And tensors can now both modify the magnitude of v, so it'll have a different length, but also its direction. And in fact, it can point in a completely different direction and have a completely different magnitude. So what is a tensor? It's just in three-dimensional space, it's just a 3x3 matrix. We can write our vector as a column vector of the three components. So we multiply a 3-element column vector by a 3x3 matrix, and now what happens is any one of these components can leak into the x component and y component and z component of this composite vector. So we're just thinking of a tensor as a generalization to a scalar that can not only change the magnitude but also the direction of a vector. And it's a 3x3 matrix to do that. Next, we want to look at reflection from an interface. So previously we talked about refractive index. That is a complex number. The real part is the ordinary refractive index, and that describes the speed of the wave. And the imaginary part is called the extinction coefficient, and that describes the loss or decay of the wave. And in the case of gain, it would grow exponentially. So if we look at reflection from an interface, here we have an equation for the reflectance. So this is power reflectance. And the interesting thing here is that both the refractive index and extinction coefficient occur in that equation. That actually means that the refractive index can stay the same, but if the loss is different on either side, we're still going to get reflections. And also, if the loss doesn't change, if the refractive index does, we also get reflections. This is also a review from a slide we did in lecture 2, I believe, electromagnetic principles. We have refraction at an interface described by Snell's law, and we also have what are called the Fernell equations that describe how much of the wave gets reflected and transmitted at an interface. And what we can see through these equations is that it is a function of the impedance on either side, so eta 1 and eta 2, and also the angles, theta 1 and theta 2. And we can see we have different expressions for TE and TM, so the amount of reflection interface also depends on polarization. So polarization and it does not matter for refraction. Snell's law is polarization independent, but how much of the way reflection transmits very much depends on polarization, the material properties on either side, and the angles. The other thing about these equations is that these are for isotropic materials on either side of the interface. If the materials become anisotropic, our equations change. So let's look at Maxwell's equations in anisotropic materials. If the material is anisotropic, the relative permittivity is a tensor, and possibly the relative permeability is a tensor. And it can be one or order of the both, but usually it has to be both at the same time. But very often the permeability tensor is so weak that we still treat this as being isotropic. But the permittivity and permeability become tensors, 3x3 matrices. So I can write Maxwell's equations now in a slightly different form. Same equations, but it's a sort of matrix form now, where we're storing the fields E and H in column vectors, and now the 3x3 matrices make a little bit more sense how they play with the field quantities in the curl equations. There are three broad categories of anisotropic materials. We can always choose our axes that correspond to the crystal axes of the anisotropic material. When we do that, there's only 3 degrees of freedom that we have. All of our dielectric constants in this case will fall along the diagonal. And this always has to be the case. We can always choose 3 axes that will make our dielectric tensor diagonal like this. We only get the off-diagonal terms when we rotate our coordinate system. Then suddenly those off-diagonals appear. But we live in a 3-dimensional world. There are only 3 degrees of freedom in a tensor. We only get the other ones when we rotate coordinate systems. Now when all 3 elements down the diagonal are equal, that's an ordinary isotropic material, and in fact we don't have to keep the dielectric constant as a tensor. We can just use it as a scalar, and in fact it's best to do that. When 2 of the elements along the diagonal are equal and the third one's different, we call that uniaxial. Then when all 3 are different, we call that biaxial. So let's now assume that the permittivity and permeability are what we'll call diagonally anisotropic. So we see the dielectric constant is anisotropic, but there's only terms along the diagonal. And the same with the permeability. So what that means is we've chosen the coordinates for our model to be the same as the axes of those anisotropic materials, and it happens to make them diagonal. The next thing we can do is incorporate some loss. So we still have these tensors, but we can build loss in. Not a problem. And we can have loss associated with the dielectric constant, and we can have loss associated with the permeability. So let's reconsider the Fernell equations. The Fernell equations are derived through applying the boundary conditions at an interface. And it's not too bad of a derivation, but it is a little bit long. It is much uglier to do this for anisotropic materials. So I don't want this to be an electromagnetics class, so we're going to skip right to the conclusion. For something that is doubly anisotropic, where mu and epsilon are equal, and they have elements down the diagonal A, B, and C, we can write Snell's law and the Fernell equations for this particular special case of anisotropic materials. So Snell's law reduces to this, and we have the square root of BC in place of the refractive indices. And now our Fernell equations for the reflectance, I didn't provide the transmittance here, but for the reflection, we get these two equations. So we still see we have angle dependence, we have material dependence. So it's not clear yet how this is useful, but it will be. Some final notes to remember about an interface. It's a change in impedance that causes reflections. Snell's law quantifies the angle of transmission relative to the angle of the incident wave, and it's the same for any polarization. The Fernell equations are what we use to quantify how much of the waves get reflected in transmission. And so it depends on a lot. It depends on the angle of the wave, depends on the polarization of the wave, depends on the material properties on either side. And the last note that I forgot to make in a previous slide is that if you have two isotropic materials, it's only possible to have zero reflection for one angle of incidence, one polarization, and one frequency. As soon as you come in at a different angle or change frequencies or polarization, suddenly you would get reflections. But it is possible, if you just have one wave at one angle, one polarization, one frequency, that we could choose the materials on either side to eliminate reflections. Now we're ready to start talking about what we call the uniaxial perfectly matched layer. So let's get right into that. And I provided the reference at the bottom that I believe was the first time this was discussed, at least close to how I'm presenting it. So here's our boundary condition problem that I described earlier. We have some device in the middle of our grid. We're going to provide it some source wave that's going to hit our device, and then it's going to scatter all this energy into potentially all these different directions. So the question is, when these waves hit the boundary, what's going to happen? Well, if we don't do anything, they're probably going to reflect back in, and that's artificial. We want this to look like this is in the middle of outer space, and those waves just go off and keep going and don't reflect back into the problem space. So we have to do something at the boundaries to ensure that. That's where the perfectly matched layer comes in. So we can't have an infinitely sized grid, so the idea is let's just put in some loss into the outer regions of our grid and absorb the waves. All that seems wonderful. However, remember from that original reflection equation that loss also contributes to reflection. So while we may be absorbing the wave a little bit, we actually introduced new reflections. So that's a problem. So what do? We introduce loss to absorb the wave, and we go back and remember what caused reflections to begin with. It's a change in impedance. So what we have to do is introduce loss, but at the same time tweak the real and imaginary parts of dielectric constants so that the impedance is matched across the interface. And if we keep the impedance the same throughout it, but introduce loss, now we can effectively absorb our outgoing waves. So the question is, how do we do all that? Let's also go back to the original Fernell equations for isotropic materials. And what we'll do is we're interested in eliminating reflections. So we set those two equations equal to 0 and figure out under what circumstances we can possibly do this. We want 0 reflections for all polarizations, all angle of incidences, all everything. We want it to always be 0. So when we set these equations to 0, that really means the numerator, which has a difference in it, equals 0. And we can solve for our conditions where we're going to have 0 reflections. Unfortunately, we have both angle terms in there, both impedances, and we can't ensure 0 reflections for all angle of incidences because it's still in these equations. It would have to drop out somehow for that not to be the case. So we have more trouble. So this is where the anisotropy comes in. And it turns out they have different Fernell equations, and this is going to make all the difference. So even if we're not modeling anything anisotropic, in our boundaries, we're going to introduce loss and adjust our impedances in diagonally anisotropic media, and what we'll see is because of these new Fernell equations, we can actually choose the material properties in the boundary to eliminate reflections for all polarizations, all angle of incidence, and all frequencies. And that's what we're after. So here's how we're going to set up our problem. Imagine a wave traveling left to right. So the green arrow here is the applied wave, and this line is our surface normal, and left to right is the positive z direction, so we have a wave coming in at some angle. Some of that's going to reflect, and some will transmit. It's going to transmit at a slightly different angle due to refraction, so we give that angle theta 2. But ideally, what we want is 0 reflection and 100% transmission. And of course over here it's going to be our Pmla. We're going to have to also introduce loss and keep impedance matched. But our goal is to have 100% transmission and 0% reflection independent of any angle, frequency, or polarization. So we want to keep the impedance matched from the problem space into the PML. The easiest way to do that is just to set the permeability and permittivity inside the PML, set them equal. So as long as they're equal, their ratio, which makes a little bit less sense with tensors, but their ratio is going to always be 1, and that will always match to free space. So we're going to make the mu and epsilon tensors the same thing, and so we'll just call it S, and we're going to make it diagonally anisotropic with A, B, and C. And now we have to figure out what do A, B, and C need to be to make this all work. So the first thing, we are going to choose, remember this was our Snell's law. We're going to choose B and C such that the square root of their product is always going to be 1. When we do that, that means theta 1 will always equal theta 2. So by choosing square root of B times C equal 1, we eliminate refraction. So angles aren't different anymore. And so also when we do this, our anisotropic reflection equations reduce to what we have on the right. So there's no refraction, so the angle terms go away. So they're a little bit simpler, and we can start whittling away at these to have 0 reflection for all angles, all polarizations, and all frequencies. But the important thing is here, nothing's a function of angle anymore because there's no refraction. Now what we're going to do, notice in the numerator of these equations we have essentially an A minus B and a B minus A. Well, if we choose A to equal B, then both of these equations go to 0. So in other words, we have no reflections for all cases. There's no angles in those equations anymore, frequency, material property, nothing. So we've ensured that our reflection will always be 0 for all polarizations, all frequencies, and all angle of incidences. How did we do that? We made the material diagonally oh man, sorry, just went to the next slide. We made our materials diagonally anisotropic. We made square root of B times C equal to 1, and we made A equal to B. Okay, so now let's look a bit at what we need to do with A, B, and C. So here we are. Here's our tensor, and we could summarize those two conditions into one equation. A equals B equals 1 over C. So now that we have these constraints on A, B, and C, we really can write our tensor as something that's uniaxial, where two terms are the same, that's the A and the B, and this third term is different, but there's the constraint that it's the reciprocal of A and B. So let's just write this as S sub z with an S sub z inverse here. And this is the tensor that we would need to absorb a wave at a z-axis boundary. Since we're absorbing a wave at a z-axis boundary, let's further call this tensor S sub z. A little bit of a redundant reuse of terms here, but as long as we have the square bracket around that, we know we're talking about a tensor. If there's no square bracket, we know we're talking about the individual scalar quantity. Now, these need to have loss, and we also need to tweak the impedance. So loss comes in through imaginary numbers in the frequency domain. So these are complex numbers, and S sub z is going to have a real part and an imaginary part. This minus sign comes in through our sign convention. We're choosing the e to the minus jk to z sign convention, so the minus there would make a positive beta correspond to loss. Important thing is S sub z is a complex number. The other thing, we have in 3 dimensions, we have, what is it, 1, 2, 3, 4, we have 6 boundaries. So we have 2 along x, 2 along y, and 2 along z. So it makes sense then that we're going to need 3 tensors. 1 for the z-axis boundaries, 1 for the sy boundaries, and 1 for the sz boundaries. And if I stepped you through all the previous slides we just went through, we would end up with these 2 tensors. Notice the one that's reciprocal is in a different position. So for the x-axis boundaries, the reciprocal is in the first position. Y-axis boundaries, the reciprocal is in the second position. And of course our z-axis boundaries is in the third position. Well, if we want to do all this at the same time, potentially, we can just multiply all these together. And we get one overall tensor quantity of this form. So now we can calculate S sub x, S sub z, S sub y separately, and then just multiply them all together to come up with this magical diagonally anisotropic material that will absorb our waves, but also prevent reflections going into it. So here's what it looks like. It looks like a box, and if you're using a grid made of points, maybe the outer 20 cells or so at each boundary, you would start building in this loss, or this Pml, to absorb the outgoing waves. These S terms in the problem space are just going to equal 1, and you'll see why that is in a little bit. It's only in these boundaries that they become something other than 1 and become complex in order to introduce the loss, but also prevent reflections. So inside the problem space, those S terms are 1. In the absorbing regions, there's something other than 1, and they're complex. So let's talk about how we actually calculate those terms. So we're going to learn a lesson from ordinary materials, and ordinary materials have loss primarily through conductivity. So let's make up a fictitious conductivity that we'll call sigma, and since we have 3 axis boundaries to worry about, x, y, and z, let's come up with a fictitious conductivity that will introduce loss at the y-axis boundaries here, another fictitious conductivity that will introduce loss on the x-axis boundaries, and if I was showing a third dimension here, we'd have sigma sub z. I put the little prime superscript here to show you that this is a fake conductivity. It's not a real conductivity you get from materials. This is something we're going to use just mathematically to introduce the loss numerically. So there's no physical material out there that would have these properties. We're making them up. So inside the problem space, where we don't want artificial loss, we're going to set these fictitious conductivity terms to 0. We only want this fictitious loss to occur in our boundaries. So the conductivity terms will be 0 in the problem space, and then something greater than 0 in the outer regions. So it turns out there's a whole science to this, and what I'm showing on this slide is one very good way of calculating these PML parameters. The important thing to realize is that we don't want to go from our problem space immediately into a big time PML with big numbers introducing lots of loss. So we tend to taper into it. That first cell in the PML we'll only have a little tiny bit of loss. And then the next cell is going to have a bit more, the next cell is going to have a bit more, until finally by the end of the PML, at the very edges of the grid, we're going to have a lot of loss. And so that tends to work very well. So first, we really were sort of pretending that these PML tensors were a mu and an epsilon. So it makes sense that we would just multiply it by mu and epsilon to stick it into Maxwell's equations. So in other words, it's going to sort of modify mu and epsilon, build in loss into those around the outer sides of your grid. But it's the same S. Once you calculate S once, we reuse it for both of the curl equations. We modify mu and epsilon the same way. Okay, so our PML terms have potentially some amplitude, some maximum value, if you will. We're just going to make the real part 1, and here we have the imaginary part. And we put it in this form. This is very similar to how loss is incorporated, or the conductivity is incorporated into a complex dielectric constant. We're borrowing from that. So this amplitude is really grading the severity of the PML, if you will. So it's going to start off as 1, and it's going to get larger from there, according to this ratio. X is distance into the PML. So at the very start of the PML, that would be 0. And the big L term is the length of the PML. So x is going to go from 0 to L sub x, and then we're going to divide by L sub x. So this ratio inside the parentheses just goes from 0 to 1. It's 0 at the beginning of the PML and 1 at the very edge at the outer boundary of the grid. So we have a number going from 0 to 1. We raise it to some power p, and that gives it some kind of parabolic or curved profile instead of linear. And now we have our amplitude terms. They go from 1 and then increase through some curve up to some other value. We have our fictitious conductivities, and it's following this fancy sine squared profile. Again, we have this ratio of x over Lx. That ratio is going from 0 to 1, and then we're multiplying that by pi over 2. So the argument inside the sine squared here is going from 0 to pi over 2. Then when we do the sine squared, we get some other profile that somebody with a lot of time on their hands figured out that works really well. And it turns out this does work really well. And here's the specific numbers that I found to work well. A max, I guess you don't want it to be 0 because then we wouldn't really have a PML. But somewhere between 0 and 5 I found to work good. This power, somewhere between 3 and 5 I found to work good. And the max fictitious conductivity in these equations to be 1. So what we're going to do, if you remember at the beginning of the semester I said for the most part don't create separate functions. Write your code as one single file. This is going to be one exception this semester. We're going to write a separate function which calculates all of your PML stuff across the grid. So when this function's done running, you'll be able to plot Sx and Sy to the screen and see your PMLs. And it's going to have two input arguments. The size of the grid. Your grid might be 200 points by 100 points. And the size of the PML on all the boundaries. The first number will be how many cells on the x low side, or at the x equals 0 side, the x high side, the y low side, and the y high side. So in a two-dimensional grid, you've got 4 sides that you can place PML terms. That's how many on all sides. When one of those are set to 0, that means you're not placing a PML there. So clearly, for some reason, we don't want a PML on the x-axis boundaries, but we do want a PML on the y-axis boundaries, and we're going to make it 20 cells each. So you hand those arguments to this function you're going to write called calc_PML2D, or calculate the perfectly matched layer for 2 dimensions, and it will hand back Sx and Sy. In this case, there's no S sub z coming out because this is just 2 dimensions. We're in the xy plane. So that'll be a homework assignment, to write that function. And all the equations you need are on this slide. And I'll also provide exact values for P and A max and sigma max that you'll need. So if we were to visualize the fictitious conductivities, they would look something like this. And if we visualized Sx or Sy, it would still look something like this. Here the conductivities will be 0 in the problem space, and then go out to something much larger at the edges. The Sx and Sy terms would be 1 in the problem space, and then go out to something else and complex in the boundaries. But notice on these slides that the loss increases gradually. That's a real key thing. And a lot of people have played around with profiles of how to do that. How do you taper into that to get the PMLs to work much better? So what I provide you works good to great, but not excellent. There's other things out there that actually work much better, but it's more sophisticated. The last thing I want to mention is the industry calls the PML a boundary condition, but make no mistake, it is not a boundary condition. It's not a numerical boundary condition or a physical boundary condition. The physical boundary condition being something like tangential fields continuous across the interface. This clearly is not a physical boundary condition. A numerical boundary condition, we're talking about an equation at an outermost cell in a grid that needs a term from outside of the grid that isn't available. And so how you handle that is what's called a numerical boundary condition, or just boundary condition when we're talking about modeling. So the PML is routinely called a boundary condition, but it doesn't answer that question. What do you do about that term you need from outside the grid? It doesn't answer that at all. This is just a way of incorporating loss into the outer few cells to absorb the outgoing waves. So in fact, even when you do this, we still have to have some kind of boundary condition, some way to handle when we need values from outside. The most common thing is to use what's called a Dirichlet boundary condition, where we just assume whatever's outside the grid is 0. And if our PML is working very well, it should be darn close to 0, and that's a pretty good approximation to make. Okay, so let's talk about incorporating these, the PML into Maxwell's equations. So we had this lesson where we derived the PML terms S, kind of pretending it was a dielectric constant. So it makes sense that they're just going to multiply mu and epsilon. So we just stick them in right there, no problems. Then we're going to assume that we have only diagonal tensors. Most materials, most devices of interest do use just isotropic materials, so this is not a very severe approximation. It's just that there's other subtleties to handling anisotropic materials that I don't want to go into right now. But if you're curious, I would be happy to answer that in class. But we are going to retain at least the possibility of having 3 different elements going down the diagonal. We just have to keep the off diagonals 0. But we can choose different numbers for the diagonals. That's not a problem. We need to do this anyway to incorporate the PML, so we'll keep this in our formulation as some extra freedom, where we could potentially at least put in a limited set of anisotropic materials. So we expand Maxwell's equations with the PML, with diagonally anisotropic mu and epsilon, and we get our final equations that we have at the bottom. So those are our 6 Maxwell's equations that we should be quite familiar with by now, but now they have the PML terms in there. So one of the reasons that I like the uniaxial perfectly matched layer is that it lets me formulate and code and test an entire algorithm without considering anything about a PML. I just build in ordinary mu's and epsilons, I can test it, get it working, and then all I have to do to include a PML is right after you build the device on the grid, but right before you model it, you just modify your mu's and epsilons to build in the loss on the outside. So you add one little segment of code, And the same code that you wrote before, not considering anything about a PML, suddenly has a PML. So that's pretty cool. That's really simple, and that's how I like to do it. So that really is it for the PML. This is a bonus section where I'm going to step you through a stretch coordinate PML, and you'll see it's really a generalization or an extension or an alternate form of the uniaxial PML to have this make some sense. The stretch coordinate PML really is state of the art right now, but it's a little bit. If I were to jump right into the stretch coordinate PML, it's more difficult to understand. So what we did is a uniaxial PML. So here's a repeat of that. We stuck it into Maxwell's equations right next to mu and epsilon, and that's how we defined our S, or the PML parameter. So instead of multiplying mu and epsilon, let's bring this PML term out from the right-hand side to the left-hand side. So now we have to invert that tensor. And really what we're going to do now is associate it with the curl operator, or that del operator. No longer, we're not going to build it into mu and epsilon anymore, we're going to build it into this curl operator. So the inverse of S times the curl operation is what I'm drawing here. This matrix is the inverse of the PML tensor, and here is our curl operator. So now we do the matrix math, we multiply it all out, and here we are. So we've taken S out of mu and epsilon and put it into our curl operator. Notice, this is just a repeat of what we had on the other slide, but I did some highlights here. Notice we have an S sub z multiplying the dz, sy multiplying dy, another sz multiplying dz, and so on. So we always have SZs multiplying DZs, and SYs multiplying DYs, and SX multiplying DX. This is a scaling operation. It's a little bit weird because these are complex numbers. We're scaling into a complex space, but it's just a scaling operation. And this is where we get the stretching term from. We're stretching our coordinates, but we're stretching into this imaginary space, which is kind of crazy, but the uniaxial PML is a very physical thing that we could understand, and now we can kind of see this comes out of that. So what's typically done in a stretch coordinate PML is that we retain the stretching terms, but we drop these. So this now is our new tensor for the curl operation with the stretching terms in there. And a little subtlety here is we have different stretching terms for the curl of E versus the curl of H. We have a complex conjugate. So that is a stretch coordinate PML, and that is the end of this lecture.